Welcome to Praise News. My name is Miles McSock. Today's hot topics: cats, why we need cat videos for our sanity. And our top story today: why quantum computing will change the world we know. Joining us is Professor Braunsfeld from the Irish Centre for High-End Computing, which is a part of the European HPC program PRAISE. Good morning, Ms. Braunsfeld.
Oh, good morning, Mr. McSock.
There's a big hype around quantum computing. Will it change our near future?
Well, we can say that there will be applications that will benefit from these new technologies.
What can we already do with them?
Right now, in our team, we are working with pattern matching algorithms and trying to improve its performance with quantum computing. Let's start with the basics. Quantum computers store information in qubits. Each qubit can store a 0, a 1, or a 0 and a 1. This phenomena that allows qubits to store zeros and ones at the same time, it's called superposition. You maybe have heard about Schrödinger cat, a cat who was inside a box, alive and dead at the same time. So imagine that alive is represented by a 1 and dead represented by a 0. We know that a cat cannot be alive and dead at the same time, but it's only when we open the box that we know if the cat is alive or dead. It's only when we measure that we resolve superpositions and we are forcing the qubit to be a 0 or a 1. This property allows to store more information compared to a classical computer. The memory capacity grows exponentially instead of linear. If we put n qubits together, we can get an n-qubit quantum circuit. This circuit will allow us to do operations. We can put a qubit into superposition with a Hallmark gate. We can also flip a qubit. If it's 0, it's going to turn into 1, and if it was 1, it's going to turn into 0. That would be done with a Pauli X gate. We can flip a qubit depending on another one with a control NOT gate. Do you have any question?
All of these concepts sound non-trivial. How are they applied to your research?
So, all these properties of quantum computing are reflected when we encode our patterns into quantum circuits and later on when we compare them. When encoding, we want to put a string into a quantum circuit. First of all, the information needs to be translated into binary. For positions, 0, 0 for the first one, 0, 1 for the second, and so on. In the example, there are two values, hyphen represented by 0 and m by 1. We want to encode the string hyphen m hyphen m. This is how the binary representation would look like. Let's go step by step. The qubits that represent the positions in the string are going to be in superposition. The qubit that encodes the value is initialized at 0, encoding for hyphen. First, we encode the m in position 2 using quantum gates. And with slightly different quantum gates, we can encode m in position 4. Because we initialize all circuits with values at 0, we know that if we apply the same operations in reverse order, we would obtain a circuit that measures 0 for all values. Let's see a demonstration. We have the circuit with hyphen m encode. First operation, get m in position 4 reverse, and then so does the second m. At the end, we have a circuit that has all values at 0. Let's see an example comparing hyphen m with m, obtaining a circuit that measures 1 for all values. When we want to compare two strings, we will put the two circuits together, one of them reverse. More or less, as more values measure to 0, the more similar the two strings are. I hope everything is a bit more clear now.
Yes. How does your work routine look like?
Let me show you. Wait a moment. Actually, 4 results are coming in.
So I'm seeing you have a lot of work to do. Thank you very much for your time and have a nice day. And now, the weather forecast for tomorrow's laundry day. Laundry day? Oh, for sock's sake.